Okay, so everyone turn to page, and this is in the white book, page 74.
Yeah, are you Felix's class?
Okay. So we're going to hang out with Tyler and we're going to fill in the boxes and the blanks and all those kinds of things. All right. So, and please do let me know if you need me to pause so you can copy something down, because I don't have a copy, so I don't know where the blanks are, because I did not make enough copies. I made just enough for each and every one of you to have one, but not enough for me. I got to make another one this afternoon. Okay. Here we go. Now, he said something wrong there. He said the atoms that make up this salt are going to come apart. What should he have said? The ions that make up the salt are going to come apart, because atoms are, by definition, neutral. Okay? What kind of a mixture is that? Homogeneous. Okay? So what kind of forces are being broken there? You've got a whole bunch of sugar molecules all stuck together. And now the sugar molecules are separated from one another. What kind of bonds or forces had to be broken? Tell your partner. Baran, you wanted to answer? Intermolecular forces. And actually, new intermolecular forces have formed between the water and the sugar. Okay, and we'll look more closely at that in just a little bit. What things would have to break in order for that to happen? Covalent bonds would have to break, okay? And that does not happen. The covalent bonds stay intact. Now, Tyler doesn't use these words, but if you look on your sheet, there are different words for how the two substances dissolve. See if you can find them and tell your partner what they are. So what is it called when those positive ions and negative ions split apart from one another? When the positive ions and negative ions split apart. That is called dissociation. Are you familiar with the word associate? Okay? If you associate with someone, you get together and you meet with them. Yes? So associating is coming together. Dissociating is breaking apart. Okay? And dispersion just means kind of scattering. Okay? So all the sugar molecules were get together and now they are scattered throughout the solution. So that's dispersion. So we have dissociation, the splitting apart of the ions, dissociation and dispersion. And that, we're going to now go to this one here. So here we have older Tyler without his little cutouts, and he's got like things here, and he's got a beard. All right, so we're just going to appreciate the little difference there, and we're going to watch what happens. Okay? Did you guys miss anything? Yeah, let's go back then. I just noticed people were looking around. Okay. So we have water is the solvent and sugar is the solute. Is there anything else you missed? Okay, so we're good? What? Oh, water. I think it says solvent. I think it's the solvent. Let's take a look. Water is the solvent, yeah? Yeah. And besides which, if it was something else, it's not that important anyway. Okay? Okay, so that's one sugar molecule, and we're going to see it up a little closer, but it's a very complicated structure. You can see it's got 12 carbons, 22 hydrogens, and an oxygen. Okay, so it's very complicated. You will never have to draw that sugar molecule. Okay, maybe if you take some higher level biochemistry courses in university, but you're not going to have to do it here. Okay. So here is the Lewis structure, okay? And you can see it's really complicated. We have a carbon ring here with an oxygen in one corner and another carbon ring with an oxygen in one corner. That's generally what sugars look like, okay? They've got these oxygens in one corner. They sometimes have OH groups coming off the side, those hydroxyl groups, okay? But like I said, super complicated. You're not going to have to draw it. Yeah? Okay. We also call it a space-filling model, okay? The 3D model is also known as a space-filling model. Do you remember which end of water is slightly positive and which end is slightly negative? Tell your partner. The hydrogen is slightly positive and the oxygen is slightly negative. And if you have trouble remembering that, well, if you draw an H, you can almost make two positive signs. Yeah, so there you go. All right. Oh, now, before he carries on, we're going to take a quick look at the sugar molecule and the water surrounding it. So if we look here, you see that red? That is an oxygen. Okay, the red is an oxygen. And oxygen in sugar will also be negative, just like it is in water. Oxygen tends to be, it's really good at pulling electrons towards itself. So it tends to be negative no matter where it is. Okay? Not always, but most of the time. So oxygen tends to be negative. And do you notice what end of the water is pointing towards that negative oxygen? The positive hydrogens. Absolutely. Okay. And if we look here, we've got a little white hydrogen, which will tend to be positive. And what's pointing towards it? The negative oxygen. Okay. So that's how they are interacting. And now you have intermolecular forces between the water and the sugar. Okay. Which is why it's able to grab that sugar and pull it away from the other sugar molecules. Okay. Oof. Now, this is where we got stuck in my other class, and it just started having a little circle that went around and around. So we are going to stop here for the moment, and if we have time at the end of class, we'll watch the rest of the video, okay? Because we didn't have time to finish it with the other block, and I want to make sure we cover the other stuff we covered with them, okay? Otherwise, the rest of this video will be for homework, all right? But we might have time to finish it because we won't have a fire bell. Fingers crossed. So for now, we are going to go to actually just any old piece of paper. Yeah, okay. Or actually, no, we are going to go to 1.5a on page 67, page 67. And we're going to finish off this page here. Are we? Are we? Did I? No, I didn't. Never mind. I don't know what I'm talking about. Sorry. This is what happens when my lesson plan gets like derailed. It's hard for me to keep track of. Okay, so what we're going to do then is we're just going to go free form on notes. So if you have some paper, if you don't have paper, there's free blank paper at the back. Okay. Now, what have I drawn here? We've got alternating positive, negative, positive, negative, positive, negative, positive, negative. That is an ionic crystal lattice. Okay, so for example, perhaps this is NaCl. And now we're going to draw in a little water molecule. Okay, so here's our oxygen, which is slightly negative. And then I don't have room to draw the slightly part. These are my hydrogens, which are slightly positive. So I'm just going to draw them as positives here. Oh, there we go. And this is why we have pretty pictures drawn in our workbook, because I cannot draw. Okay, so that's a little water molecule. And let's assume we have lots of water molecules. I'm only going to draw one because that was painful enough to watch me draw that one. Will lots of water molecules be able to lure, to like entice the ions away from the other ions. So once you got that written down, you can have a little chat with your neighbors. All right, what do you guys think? Yes or no?
Yes.
Yes. Why? Yes. The water separates the ions from each other and we will get interactions. You see how we've got these positives? Those positives will attract. Whenever I draw these kind of like red dashy lines like that, that's always the attraction. Those positives are going to attract that negative. And just like we saw in the video with the sugar and the water, we will eventually end up with this negative ion being surrounded by waters, where we have the positive hydrogens pointed towards that negative ion. So we have the anion and it gets surrounded by the slightly positive hydrogen end of the water. And if you're like, how did you draw that delta? Remember, it starts here and it goes around and it goes up and then starts here, goes around, goes up, and then starts here, goes around, goes up, and then yes? I thought I'd get a chuckle for that, but I did not. I'm so disappointed. It's okay. It's okay. All right. So that is what happens with an anion. Could you guys draw me what happens with a cation? Okay, so I'd like you to draw what happens with a cation. So did you end up with something that looks like this? Excellent. So we have the cation, and it gets surrounded by the slightly negative oxygen end of the water. So this is why salt is soluble in water, because water has charges that are attractive to the ions. So water has charged areas which are attractive to the charged ions. Excellent. Okay. Did anyone go home last night and try and dissolve salt in oil? This suck. Sorry. Go home and try it tonight, okay? But we're going to do a little thought experiment here, okay? So I'm going to show you approximately what oil looks like. Oil is a little more complicated, but oil looks approximately like this. Okay, so we have a big long chain of carbons all attached to one another. Yes? Now, how many bonds does carbon have? 4. So this carbon on the end needs another 1, 2, 3 bonds. And what's going to go on the outside of that? Barring anything else, it's going to be hydrogen. Okay? And all of the middle carbons, they each are already bonded to 2 things, so they need another bond on the top and the bottom to give them 4 bonds. And so we're just going to go along and fill in all the rest of the bonds with hydrogens. Like I said, that's not really what oil looks like. This is just an alkane, okay? It's just a plain carbon-hydrogen compound, but it's close enough, all right, to what an oil looks like for us to think about it and do this thought experiment. So what I'm going to ask you is, does this molecule have a positive and a negative end? And when we say if it has a positive and a negative end, i.e., is it a polar molecule? And while we're here, I'm going to explain what IE means because probably most of you don't know. Okay, IE stands for, the Latin is id est. Id est. And the id means that. And the est means, anyone guesses? Anyone who's taken French or Spanish or is, that is. That is to say. Okay, so IE means that is to say, which another way of saying that would be to say, in other words. So IE really means, in other words, a polar molecule. Does it have a positive end and a negative end? In other words, is it a polar molecule? So I would like you to have a little chat with your neighbor about that and decide what you think about oil. Is it a polar molecule? Does it have a positive end and a negative end, or is it non-polar? No positive end and negative end. What do you think? I hear one not a polar molecule. Anyone want to agree or argue? Nobody wants to agree? Nobody wants to argue? You're all like, I don't know. You don't even want to take a guess? Okay, I got to tell you something. Okay, I'm going to tell you a little story because I told my other class the story. All right, and there's a certain thing, it's called intellectual risk taking. Now, this is not the kind of risk taking where you go out and you do crazy things. I just watched this video and it had these people and there was this guy and he literally stepped off like a 3-story building and there was a lamp post 10 or 15 feet away from the building and he sort of jumped off and then he grabbed onto the lamppost and slid down. And I was like, okay, that's one kind of risk taking. Then there was this other guy who jumped off this cliff and did all these spin, thousands of feet down. Okay, not thousands of feet, but maybe 50 feet, 100 feet, who knows. Anyway, it was a long way, went into the water and I was like, that's not the kind of risk taking we're talking about here. We're talking about intellectual risk taking, all right? Yes. It is non-polar, yes. Okay, now I'm going to finish my story about the intellectual risk-taking though. I had a student, and this was in my first year teaching 11 Enriched and 12 AP, and this student's name was Allison, and Allison, bless her, she answered all my questions. Every time she would answer a question, okay? I asked a question, she would answer it. And you know what happened every time she answered the question? She got it wrong. Every time she got it wrong, okay? We used to laugh about it, right? Because she would try out her ideas, yes? And so then it came to the time of the AP exam. She wrote the exam. It's on a scale of 1 to 5. 1 is the lowest, 5 is the highest. What do you think Allison got? She got a 5. She had cleared up all of her misconceptions and really thought about it and thought her ideas out loud and gotten direct feedback from me, right, on those ideas and gotten them corrected. And so, you know, it's a powerful learning tool to interact not just with your partner, like your partner is a good place to start, right? So if you're like, I don't really want to talk about it because it's late in the day and I'm tired and that sounds like a lot of effort, I don't know, you know, start with talking to your partner. But if you're comfortable talking to me, talk to me, okay? Because we'll get a good dialogue going, all right? Okay, and that means ask questions too. Don't be afraid to show me you don't know something, because you're not supposed to know much yet because you're in like grade 10 or 11, right? If you knew all this, what would you be doing in this class? That would be crazy. Yes? Okay. Although I did have one student who took AP chemistry one year, he repeated it the next year to get a better grade, and then he took chemistry level 1 at university. And apparently he slept through all the lectures and got the highest mark in the course. Anyway, I don't recommend that. It's a huge waste of time, but you know, we all make our choices, right? Anyway, yeah. So if we look at this molecule here, what is on the outside?
Hydrogen.
Hydrogen. Is there anything different on the outside other than hydrogen? No. So it's all the same. Yes? So how is it possible that one end would be positive and one end would be negative if it's all the same? Yes? Hydrogen and oxygen. Oxygen's really good at pulling electrons towards itself, so it ends up being negative. Hydrogen is not as good at pulling electrons towards itself, so it ends up being positive. And we'll talk more about how you can know that later in a later unit. For now, you just need to know that oil is non-polar. It's got no positive end, it's got no negative end. Now we're going to shorten this structure because drawing this thing would drive me crazy. We got 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons. This dot is going to represent a carbon. And it's going to be bonded to a second carbon. Okay? And then we're going to go 3, 4, 5, 6, 7, 8, 9. Now we have 9 carbons. And we don't actually have to draw those dots. We just go 1, do, 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 do. And that is the shortcut way of drawing that big long molecule. Okay? Is that called the skeleton structure? Yeah. Okay. So that's our skeleton structure for that thing. So now what we're going to do is we are going to draw a little ionic crystal lattice. And now instead of putting this crystal lattice into water, we're going to put it into some oil. Okay? And now we will ask ourselves, oh, actually, before we do that, I asked one other thing in the other class. What do we call this little thing here? Just one of the ions and one of the other ions. That's our formula unit. Yes, good. Okay. Formula unit. All right. Will the oil be able to lure the ions away from each other? And once you've got that to your satisfaction, you can have a little chat with your neighbor about that.
Those are the questions you would say that.
What do you guys think? Yes? No? And you guys can just shake your head or nod your head. No. Okay. Anyone want to tell me why not? Jade? Pardon me? There's only one charge. There's really and in fact, to be honest with you, the hydrogen doesn't really have much of a charge, even in the in this structure, because carbon and hydrogen actually pull on electrons fairly equally. So the hydrogen is actually neutral. Okay, mostly neutral. All right, so the hydrogen is mostly neutral. So does it have anything to offer those little ions? No, yeah.
I was gonna say that I was just thinking that if the hydrogen takes away the negative ions, wouldn't that leave the positive ions just moving and they would repel each other and I would just get home?
It would, but here's the thing. If we have an oxygen and a hydrogen, okay, and I'm going to draw the bonding electrons, okay, oxygen is really good at pulling electrons towards itself. We say that oxygen is very electronegative. You're learning a new word that the other block didn't learn yesterday. Woo! Or this morning. So oxygen is very electronegative, which means it is very good at pulling bonding electrons towards itself. So if we have our bond between these two, the two bonding electrons will be much closer to oxygen than to hydrogen. And I had only given you part of the story at this point, right? So you wouldn't have known this yet, okay? So if I was to look at the electron density of that bond, what it would look like is it would look like this. We've sort of got a cloud of electrons in between there. You know how, I don't know if you learned this in grade 9 and 10, electrons are not like pinpointed in one location. They actually move around in like a space. So the electron will actually be somewhere within this area. Okay, the two electrons will be somewhere in here. And if you take a time-lapse photo of the two electrons over time, they will form a shape that looks like this, where you have a lot of density. They spend a lot of time over near the oxygen, and they don't spend very much time near the hydrogen, which makes, that is what actually truly makes the oxygen negative. Okay? That's negative. The negative with VE, negative. And they spend less time with the hydrogen, which makes the hydrogen slightly positive. Okay? And if we were then to look at a hydrogen and a hydrogen, hydrogen has, it's kind of low-ish electronegativity. So oxygen is really good at pulling electrons. Hydrogen is not so good at pulling electrons. Now, what if I bond a hydrogen to a hydrogen? Both those hydrogens have a sort of lowish electronegativity. So they're both pulling on those electrons. One's pulling this way and one's pulling this way with the same force. Yes? So where are the electrons going to end up? Right in the center. So what that means then is that the hydrogens will be neutral because the electrons are not spending time with one or the other. Okay? The bonding electrons are equally shared. They spend the same amount of time with each hydrogen. So therefore, neither of the hydrogens has a positive or negative charge. They are both neutral. I knew I should have put electronegativity in the fundamentals unit. I knew it, and I didn't do it. And I regret it now, but that's okay. We're doing it now. So if we were then to draw the electron density diagram for where those bonding electrons are, we would have a hydrogen here, a hydrogen here, and we'd basically just have essentially a sausage shape between them. Ooh, where'd you go? Why'd you close? Okay. Oh, and you didn't keep all my dots. Oh. Okay, I gotta draw more dots. There we go. So here we have an even distribution of the bonding electrons. So basically the bonding electrons are just somewhere in between the two hydrogen atoms, and they spend just as much time near one hydrogen as they do near the other hydrogen. Okay? Now, it turns out that carbon and hydrogen have very similar electronegativities. They both have a similar ability to pull electrons towards themselves. Okay? Hydrogen and carbon have similar electronegativities. They have a similar ability to pull bonding electrons towards themselves. And if that's the case, if we had a hydrogen bonded to a carbon, where would the bonding electrons end up? Where do the bonding electrons spend most of their time? Do they spend it near the hydrogen? Do they spend most of their time near the carbon? Or do they spend an equal time shared between them? An equal time shared between them. BW is between the two atoms. So once again, we would have our hydrogen and our carbon, and we would see our electron density would look like this. Okay, with that little sort of sausagey kind of shape in between the two atoms. So there's no slightly positive end, and there's no slightly negative end. It's all just neutral. Is good? Okay. So Baran, I think that would take care of sort of the idea if the hydrogens were all positive, they could take away, but they're not all positive. They're all just neutral. Does that make sense? So all the hydrogens here, because they're attached to carbons, they are neutral. Yeah? So they have nothing to offer the ions. So if this ion here then looks out at the world, if this little ion here looks sideways at its partner, yes, it says, ooh, positive, sticky. Yes? And it also looks up here And it says, ooh, positive, sticky. Yes? But if that little ion looks out at a oil molecule, which I've drawn too far away, but you get the general idea, it says, meh, no charges. Not sticky. Does that make sense? Yeah. Okay. There's an analogy I'd like to make here for you, and that has to do with like magnets and rocks. Okay? So because magnets stick together in the same way that positives and negatives stick together. Yes? But we can imagine magnets because charges are usually like so tiny we can't see them. If I took a bunch of just like separate magnets and I had them all spread out and then I just threw them into a box, what would they do? And then I shook the box a little bit. What would the magnets do? They're all separate. I throw them in the box. I shake the box a little bit. What happens to the magnets? They all stick together. Yes? Everyone do it with me. Everyone. Okay? Magnets all come together. Sticky. Yes? All right. Now let's say that I have some blue magnets, which is going to represent my salt. Yes? And I have some red magnets, which are going to represent my water because it also has positive and negative ends. So the waters are like magnets and the ions are like magnets. They both have positives and negatives. All right? But one's just blue, a blue magnet, one's a red magnet. They're the same. I throw them in a box. What happens? Everyone? Okay, they all come together, and now you have a mixture of the blue magnets and the red magnets. Okay, they still stick to each other. It doesn't matter if they're blue or if they're red. They still stick. Now we're going to take some magnets, some blue magnets, our ions, okay? And we're going to throw them in the box, but at the same time, we're going to throw some rocks into the box. Okay? All at once, throw them in, give the box a shake. What's going to happen to the magnets? What's going to happen to them? Show me. Right? If you get a little shake, right, the magnets are going to be like, ooh, a magnet. And they're going to go jump towards that magnet. Ooh, another magnet. And they're all going to glom together in one thing. And what's going to happen to the rocks? Where will the rocks be? They'll just be on the outside of the magnets. Yes? And if there's a rock in between and you give it another shake, that rock will eventually get kicked out because the magnets are trying to get beside each other. Okay, because that's the most stable position for the magnets to be in, is right beside each other. Okay, and that's exactly what happens with this ionic crystal and the oil. Those ions are like the magnets and the oil is like the rocks. The rocks have nothing to offer the ions, so there's no draw to pull them away. Yeah? So the oil is like the rocks, and the ions are like the magnets. Whoops, I forgot a vowel. I'd like to buy a vowel. Do you guys even know what that means? No. There used to be a show called Wheel of Fortune. Has anyone heard of Wheel of Fortune? Okay, so in Wheel of Fortune, you would like spin the wheel and you would get like some money or whatever. I don't know. I didn't watch it very much. It wasn't that entertaining of a show, but they'd be like, ooh, I would like to buy a vowel. And it was like fill in the blanks. It was like Hangman. essentially. Okay. And so you could buy a vowel because getting a vowel was, but you had to spend some of your money. Anyway, there we are. So I needed to buy a vowel because I forgot the A in magnets. So that is kind of the same amount that I covered with the other block. It's not the same stuff. What I'll do is tomorrow with them, I'll cover the stuff that I didn't cover with you and vice versa. You will write your quiz. There will be time though at the end of the quiz to cover the same material. Shall we finish watching the Tyler video? So you don't have to do it for homework? Okay. So let's go do that. There we are. Okay. So this is on page, what, 60 something? What page are we on? 77? Awesome. 77 in your white booklet. That's okay. Let's go back. There? Here.
Yeah, somewhere.
Somewhere in here? Okay, we'll go back to the beginning of that chapter. Okay. Here we go. Okay, so the molecules don't break apart into their atoms. Dissolving doesn't break the covalent bonds inside the molecule. Now, if you ever miss anything, the filled in version of this is in your answer key. Okay, so if you're ever like, and I don't want to watch the whole video and see it, it is in your answer key, so you can just take a look. Okay? Do you guys prefer subtitles or no subtitles? No subtitles? Okay. You guys need me to go back or are we good? We're good? Solvation, when a solute particle is surrounded by molecules of solvent. I always get a little excited during this part because I'm like, solvation, like a Southern Baptist preacher, you know? Solvation. We good? Now, I think we're like just about out of time. Yes? So, homework, finish watching this video, okay? And study for your quiz. Yeah? So just finish watching the video, filling in the thing, and watch the quiz. And if you're like, where do I get the video from? You go onto your sheet and you say, I am here. And you go here, and you can either have the QR code or the link. Yes? So those will both take you to the video. Phew.
So with tomorrow's quiz, like it doesn't take a whole entire.
It shouldn't take the whole block. If you know what you're doing, it will not take the whole block, right? If you're like desperately trying to think your way through each question because you haven't practiced enough, it might take you the whole block, but I'm not going to give you the whole block. Okay? So don't plan on, it's like 6 questions, I think. Yeah. Something like that. Yeah. Solvation is the process. Solvated means it has been. Yeah, that's what I Yeah, you're like on. Yeah.
Okay.
Yep.
Thank you.
So we finished it all.
I wanna try.
Okay. Hepton, which is.
I'm so tired.
Oh, by the way, if anybody wants to sign out at Hepton, there are extra practice problems in here if you want to, and they are on that card there. You can grab one and fill in a book card for me. Okay, I'll grab the book card so you can have one. And let me just find the pages for you. Yes.
Yeah.
It's also on Teams, so you don't need to sign it out. You can just find it on Teams. But if you want one of them, you can grab one. Oh,
You want that back or the line pages? Yeah.
in here.
What can you do?
You think I lost your pieces? No, it's like on the bowl.
Almost 6.0. Like 6.7. Okay, so. Oh, no, diatomic is like there's always L. It's like yeah. Always okay, so if I am 24. The only thing is that if you see anything with gas and FTP, ignore it because we have. Okay. So gas. Wait. So ignore the lines. Let's just see. Something. 35. 38. Okay, but let's just see. There you go. I mean, I feel like honestly, you probably don't need it. Yeah. Yeah. That's right. So if I say it's an ion, that would be M3 minus. If I say it's an atom, it's but if I just say nitrogen, if I just say nitrogen, like if I say a word like if I write out that word, that's it. Sure.
Yeah. Yes. Let's do that. So we need to go to my email, and you're going to come around here because you're going to have to type things. Okay. And I need to go to student password reset. Here we go. Okay, and the website is here. And I click on, not that one, I click on reset password, reset student password. Okay, so let's do this. Okay, reset password. I don't want to reset my password.
Oh, my.
Can you type yours in?
Okay.
Invalid username. Okay.
I
You
think
might
it's
need to-
supposed to be your username.
Yeah, I know, but like I don't want to reset my password.
No, cause like my.
Okay,
teacher
okay. Let's try it.
said-
Okay. Enter.
You did the same thing.
Enter. What is your problem? Let's okay. I'm just gonna close it and we'll try opening it again. Oh, good Lord.
The office said they're trying to fix the website.
Yeah. I would go talk to them at the office and say, your teacher tried really hard. And in the meantime, do you need anything from Teams before tomorrow?
Oh yeah, the homework.
Oh, okay.
The test tomorrow.
Okay, so it's just anything that's in here is spoken.
Okay.
Okay. Only 5.1 and 5.2.
Okay.
Okay? So that's all I'm going to put up there is that the quiz is on 5.1. All right?
So I have a question.
Yeah.
For the periodicity,
Yes.
can I like write on the back the
Charges?
no the
Oh, the diatomics?
no
No. I'm not doing a good guessing.
no the it's like the tetra di those
Oh,
things.
monoditritetra? Sure, what the hell? Yeah. Okay, yeah. Are they even on here? No, they're not. Okay,
Yeah, I couldn't
yeah.
find
Okay. And because you came back late, like if you really feel by tomorrow morning that you are not ready, I did. Okay, so just bear that in mind because you know, it is harder than it is. So, yeah. Okay. So yeah. Okay. You too. Right there with you.
I leave Jenny's.
Absolutely, yes.
Where's the breakfast?
It's right here, it's good. Yeah. Yeah, it's cool.
Yeah. 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 I believe that's not good. Oh, yeah, so I know. It's, 6, 3. You're 26. Okay. Up, 16. Whoa. 16. 16. 2. 3. 7, 5. Okay. 6. 6. 6. 5. Whoa. Four, okay, 20. Well, 15. 20. 600. Oh my God, okay. Just later.